algebraic limits, and more. Let's start by reviewing a theorem. We know that if a function is continuous at x equals c, then the limit is equal to the function's value obtained by direct substitution. So the limit as x approaches c of f of x equals f of c. This is true when the function is continuous. But what do we do if the function is discontinuous at x equals c? Let's look at an example. Here we want to evaluate the limit as x approaches 1 of the quantity x squared minus 1 all over the quantity x minus 1. Well, the first thing that we would try is direct substitution. If I substitute in 1, the numerator is 1 squared minus 1, which is 0. And the denominator is 1 minus 1, which is also 0. Now 0 over 0 is not a real number. It's also not undefined, so we do not have a vertical asymptote here. We want to explore what is happening to this particular function by thinking about its graph. We can evaluate limits if we know what their graph looks like, so let's try to graph this rational function. So we have x squared minus 1 over x minus 1, and it turns out this is actually going to look like a line with a hole in it. And let's go ahead and understand why. When we factor the numerator, x squared minus 1, that's the difference of squares, so we get x minus 1 times x plus 1 all over x minus 1. So each of those quantities, x minus 1 times the quantity x plus 1, all over the quantity x minus 1, they're all being multiplied, so we can cancel the two linear factors, x minus 1 that's in the numerator and x minus 1 that's in the denominator. And when we cancel out linear factors like that in a rational expression, we know that what we're creating is a hole in the graph. So what we have left over is just x plus 1 in the numerator. So we have x plus 1, which is a linear function, but there is a hole in the graph at the x value that makes that linear factor that we canceled equal 0. Well, the x value that makes this linear factor x minus 1 equal 0 is positive 1. So there's a hole at positive 1. And then to find the y value of the hole, we substitute that x value into the part of the rational function that's left over after canceling. So we're going to plug 1 into x plus 1. So 1 plus 1 is 2. The hole in our graph, in our line, is going to be at 1, 2. So my rational function, it turns out, is a linear function with a hole in the graph at 1, 2. And we were interested in evaluating the limit as x approaches 1. Well, from both sides of 1, I'm getting closer and closer to the y value 2. Now there is a hole right there, but remember, limits don't care if there's a hole or a filled-in point, just so long as we're getting close to the same value. So in terms of limits, the line with a hole in it and just the line x plus 1 basically behave the same way. So the limit as x approaches 1 of just the regular old line without a hole in it, x plus 1, would still be 2. From both sides of 1, I would still be getting closer to 2, and there'd be a filled-in point there, but they behave in the same way in terms of limits. So we're going to use that fact, we're going to use that idea to come back to our original limit and evaluate it using algebra. So not having to go through this process of graphing it. Instead, we're going to use algebra to evaluate this limit. So here, I'm going to factor the numerator in the same way that I did in terms of the first step for graphing. So we're going to have the limit as x approaches 1 of, in the numerator, x minus 1 as a quantity times x plus 1 as a quantity, all over the quantity x minus 1. And we have to keep writing limit in front because we haven't evaluated anything yet. And then we're going to cancel out that linear x minus 1 in the numerator and denominator. So what we have is the limit as x approaches 1, so I'm going to write it again, of the quantity now x plus 1. So what we're saying here is that the limit of the original rational function is the same as the limit of the line x plus 1. They basically behave the same way in terms of limit values. But the line x plus 1 we can evaluate. We can plug 1 into x plus 1. And so 1 plus 1 is just 2. So that is the answer to our original limit, which we obtained by graphing and thinking about where the hole in the graph was. But we didn't have to actually consider the graph. We could have just factored and canceled that linear term, canceling out the hole in the graph, or the x value of where the hole would occur, and we canceled out basically that problem value, and now plugging in 1 doesn't create a problem. I end up with just 2 at. The last example brings us to a theorem that says, let f of x equal g of x for all x values except for c in an open interval containing c. If the limit as x approaches c of g of x exists, then the limit as x approaches c of f of x exists. And the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. So basically we have two functions f and g that are equal everywhere on an interval except at c. Well, if the limit of one of those functions near c exists, then the limit of the other function near c also exists, and they're the same value. So basically the two functions agree except for that point, so that means in terms of limits they behave the same way. Now let's look at the definition of indeterminate. We say that a function f of x is indeterminate at x equals c if, when f is evaluated at c, we obtain an expression of the form either 0 divided by 0, infinity divided by infinity, infinity times 0, or infinity minus infinity. So if we substitute in our x value, if we get any of the following, 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity, those quantities are called indeterminate. So think about it as they cannot be determined. They don't really make a lot of sense. So 0 divided by 0, or even infinity times 0, like which one is it? Does infinity take over? Does 0 take over? These cannot be determined. So now, what are some of the strategies for algebraic manipulation of limits? Well, if direct substitution results in one of those indeterminate forms, then we can use the following algebraic strategies to rewrite the function and then use substitution, because the original function and the rewritten function are going to agree at all but one point. So those strategies include factoring, or sometimes expanding and canceling, multiplying by the conjugate, and then combining fractions and simplifying. In this example, we're asked to find the limit as x approaches 0 of the quantity e to the 3x minus e to the x over the quantity e to the x minus 1. So the first thing that we try, no matter what, is direct substitution. So if we substitute in 0 into the numerator, e to the 3x is e to the 0, minus e to the x, that's e to the 0. Well, e to the 0 minus e to the 0 is just 0. It's 1 minus 1. So my numerator is 0, and my denominator would be e to the 0, which is 1, minus 1. So we have 1 minus 1 again. We have 0 over 0. So we just said what that was called. That's called indeterminate. This cannot be determined. So what I like to say is that this means, oh no, there's more work. So when I see 0 over 0, what I like to think about is after the 0 in the numerator, I think about adding the letter h, so that's like O, and then on the bottom in front of the number 0, I think of putting the letter n in front of it as a reminder. when I get 0 over 0, oh no, I need to do more work. I can't just stop. That's not the answer. Some students say, when I get 0 over 0, the answer is does not exist. That's not true. So, oh no, we have to do more work. Now, what is that more work? Oftentimes, we're going to turn to algebra. So in this case, the strategy that we're going to use is factoring. So in the numerator, e to the 3x minus e to the x, there's an e to the x in common that I can factor out. So I'm going to go ahead and write that the original limit is equal to the limit as x approaches 0. I have to remember to continue writing limit because I'm not evaluating yet. In the numerator, I'm going to factor out the e to the x, and what's left is the quantity e to the 2x minus 1. And then in the denominator, we still have the quantity e to the x and then minus 1. So currently, I can't cancel anything. So after I factor, I attempt to see if there's anything I can cancel out, and I don't have any products here of terms that are being multiplied that I can cancel. So this e to the x in the numerator cannot cancel with the e to the x in the denominator because of the minus 1 that's there. So what I have to recognize is that more factoring can be done. In the numerator, I have a quantity e to the 2x minus 1, and that's the difference of squares. So I'm going to go ahead and write the limit as x approaches 0 one more time because I still have not evaluated. And in the numerator, I have that e to the x I originally factored out, but e to the 2x minus 1 is the difference of squares. I can factor that to the quantity e to the x minus 1 times the quantity e to the x plus 1, all over the quantity e to the x minus 1. And now I have a factor in the numerator and denominator that I can cancel. E to the x minus 1 is in both and being multiplied in both. So after I go ahead and cancel those factors out, I have the limit as x approaches 0 of e to the x times the quantity e to the x plus 1. And in the denominator, I have just over 1. So now, after I've canceled, I'm going to go ahead and try direct substitution and see what happens. Well, since I'm trying direct substitution, I'm not going to write limit anymore. I'm going to put e to the 0 times the quantity e to the 0 plus 1, which is just 1 times the quantity 1 plus 1. So 1 times 2 is 2. So I end up with the quantity 2 for my limit. In our next example, we're asked to find the limit as t approaches 0 of the quotient, where in the numerator I have the square root of the quantity t plus 1 minus 1 on the outside, all over t. So here, direct substitution, we always try it. If we substitute in 0 to the numerator, we're going to end up with a 0, and if we substitute 0 into the denominator, we end up with a 0. So 0 divided by 0 is indeterminate, right? So, oh no, I have to try to do some more work. Now, the work that we're going to do here this time is multiplying by the conjugate. So we can't really factor here, and the square root is kind of a giveaway that the strategy we're going to use is to multiply by the conjugate. Now, in the numerator, I have the square root of the quantity t plus 1 minus 1. So the conjugate of that I'm going to multiply by is the square root of the quantity t plus 1 and then plus 1 on the outside. And if I multiply the numerator by that, I also have to multiply the denominator by that same thing. And now we're going to go ahead and multiply. So since I multiplied by the conjugate here, across the numerator, the square root of the quantity t plus 1 times itself, well, the square roots cancel, and in the numerator, I'm just going to have a t plus 1. So I still have to write limit. The limit as t approaches 0. In the numerator, I will have a t plus 1. While the outer and the inner are going to cancel when I multiply these binomials together. So last, -1 times +1 is going to give us -1. And now in the denominator, I'm not going to distribute the t in. So I have t times, here I'm going to have this binomial, the square root of the quantity t plus 1 plus 1. Now in the numerator, I have the quantity t plus 1 minus 1. So the plus 1 and the minus 1 are going to cancel out. And so now what I have is the limit as t approaches 0 of t all over t times this binomial where the first term is the square root of the quantity t plus 1 and then plus 1. Well, the t in the numerator and the t that's being multiplied in the denominator are going to cancel out. Now, if I cancel those out, when we say cancel, we mean they become a 1. So t over t is really just a 1. So there is a 1 left over in the numerator. So after I've canceled those, now if I try to apply direct substitution, because we have the limit as t approaches 0 of 1 over, and then this binomial on the bottom, I have the square root of the quantity t plus 1 plus 1. If I substitute in 0, now I can stop writing limit. So I have 1 over the square root of 0 plus 1, and still in the denominator, a plus 1. So I have 1 over 2. So my final answer is 1/2. In this example, we want to find the limit as h approaches 0 of this quotient, where in the numerator, I have two fractions that are being subtracted. In the numerator, I have 1 over the quantity x plus h squared minus 1 over x squared. And then all over in my denominator, I just have h. Now, if I did apply direct substitution, that's going to give us, in the numerator, 1 over x plus 0 squared minus 1 over x squared. So that's 1 over x squared minus 1 over x squared, that's 0. And substituting 0 into h on the bottom just gives me 0. And I want to be careful and substitute 0 into the value of h, because the limit has h approaching 0. So we are going to leave the x's as variables. Now we do have indeterminate 0 over 0, so that means we're going to do more work. And the more work is going to be in the numerator, I need to combine those two rational expressions together by forcing them to have common denominators. So I will start by writing the limit as h approaches 0. And then I'm going to start by writing a big quotient. So I have a fraction bar. In the denominator, I'm going to leave h. That part's fine. In the numerator, 1 over the quantity x plus h squared minus 1 over x squared, the common denominator will be x squared times the quantity x plus h squared. So I'm going to make that the denominator of each of my quotients in the numerator. So x squared times the quantity x plus h squared is the denominator for each of my fractions in the numerator. Well, then the numerator on the first fraction is going to have to be x squared. If I multiply the bottom by x squared, I have to multiply the top by x squared. On the top right quotient, I'm going to have to multiply the top by the quantity x plus h squared, because that's what I multiplied the bottom by. And now in the numerator, I have common denominators. So I can go ahead and put those two together. So I have the limit as h approaches 0. I'm going to put a big fraction bar. On the bottom, I'm going to put h. Now in the numerator, I'm going to combine the two quotients to one quotient with the common denominator, x squared times the quantity x plus h squared. And then I'm going to subtract across the numerator. So if I subtract across the numerator, I have x squared minus the quantity x plus h squared. So this is definitely a lot of algebra that's going on here. Now, in the numerator's numerator, I'm going to have to distribute the quantity x plus h squared. And remember, I cannot just distribute the exponent. So I am going to have to FOIL that whole thing out. So I'm going to have the limit as h approaches 0. And then I'm going to go ahead and have x squared minus, and if I distribute out x plus h as a quantity squared, I get x squared plus 2xh plus h squared. That's over the common denominator, x squared quantity x plus h squared. And then that whole thing is over h over 1. And I'm writing it as divided by h over 1 because the next step is going to be to multiply by the reciprocal as well as distribute the negative into the binomial that I just expanded. So where we're at here is we have the limit as h approaches 0 of, I'm going to have x squared in the numerator minus x squared minus 2xh minus h squared over x squared times the quantity x plus h squared. And now, instead of dividing that by h over 1, I'm going to multiply that by 1 over h, the reciprocal. And now, some nice things should start to happen. Some things should start to cancel out. Well, in the numerator of the first quotient, x squared minus x squared is going to cancel. And then, in the numerator on the left, I have two terms, negative 2xh minus h squared, and those have an h in common that I can factor out. So we have the limit as h approaches 0. I'm going to factor an h out of that numerator. So h times the quantity negative 2x minus h over x squared times the quantity x plus h squared. And that quotient times that 1 over h, that reciprocal. And now the h's are going to cancel and give me just a 1. So when those h's cancel, now if I apply direct substitution to the parts I have left, I'm not going to create an indeterminate form. So if I go ahead and substitute in 0 for h, the numerator is currently just negative 2x minus h. So then I have just negative 2x, because minus h would be minus 0, over the denominator has x squared, and then times the quantity x plus h squared. If I substitute in a 0 for h, I have x squared times x squared. Well, I can do a little bit of simplifying here because the x's, one in the numerator and one of the 4 that are in the denominator will cancel. So we'll cancel 1x in the numerator, 1x in the denominator, for a final answer of negative 2 over x cubed. Negative 2 over x cubed. So my answer isn't numerical, and that's because I had a variable x to begin with at the start of the problem. So my limit was as h approaches 0. That told me to substitute 0 into the h, but the x remained throughout the problem. So that's why my final answer is negative 2 over x cubed. And this strategy was combining fractions with common denominators. In this next example, we're going to find the limit as x approaches 0 of the quantity secant x minus 1 over tangent squared x. Now, if we apply direct substitution, which always should be our first step, that is going to give us secant 0 minus 1, which is 1 minus 1, or 0. And in the denominator, tangent squared of 0 is just 0. So we do end up with 0 over 0, that indeterminate form. So, oh no, I have to do some more work. And that more work might actually be a double oh no for some people, because it's going to require us to recognize a trigonometric identity in order for us to be able to use some algebra. Now, the numerator has a secant function. The denominator has tangent squared x. So what's hopefully maybe coming to mind here is the Pythagorean identity involving tangent squared. So I'm going to go ahead and say that this limit is going to equal the limit as x approaches 0. The numerator will stay the same. I still have secant x minus 1. But the denominator, tangent squared x, is equal to secant squared x minus 1. So that is from our trig Pythagorean identity. And now I have all the same trig function involved, and I can't cancel anything yet because I have a bunch of differences. I don't have products yet, right? Terms being multiplied. But in the denominator, I do have a difference of squares. So I can factor the denominator. I'm going to write limit again because I haven't substituted in yet. The numerator will stay the same, so we have the limit as x approaches 0 of, in the numerator, I have secant x minus 1. The denominator will factor to the quantity secant x minus 1 times the quantity secant x plus 1. And now I can go ahead and cancel from the numerator and denominator that same factor, secant x minus 1. Canceling those two will create a 1. So I have a 1 in the numerator. So I have 1 over the quantity secant x plus 1, and I'm still evaluating a limit. So the limit as x approaches 0 of 1 over secant x plus 1. And now after I've canceled, I want to try that direct substitution. So 1 over secant 0 plus 1. Well, secant of 0 is 1, so I have 1 over 1 plus 1, or 1/2. So we may have to stretch back and remember some of our trig identities in order to allow us to manipulate this and cancel so that we can have a function that I can evaluate with direct substitution that doesn't give me my 0 over 0, oh no, indeterminate form. In this example, we want to evaluate the limit as x approaches 5 of the quotient, where in the numerator I have the absolute value of the quantity x minus 5, and in the denominator I have just x minus 5. Well, direct substitution would give me in the numerator the absolute value of 5 minus 5, that's 0, and the denominator is 5 minus 5. So I get 0 over 0, I get that oh no situation. But there's no algebra I can perform on this particular quotient. I cannot cancel the x minus 5 that I can tell is in the numerator and in the denominator because they're not exactly the same. The absolute value bars around the numerator are not exactly the same as just x minus 5 that's in the denominator. So we can't use any algebraic techniques that we could in the previous problems like factor and cancel. So I want to come at this from a numerical approach. So let's think about what happens as I substitute in some values into the absolute value of x minus 5 over x minus 5. So let's pick some values on each side of 5. I'm going to start by plugging in, let's say, 3, and then 4, and 4.5. And I'm thinking about substituting those into the absolute value of x minus 5 over x minus 5. So if I substitute in 3, the absolute value of 3 minus 5, that's going to give me the absolute value of negative 2, which is just 2. And in the denominator, I have just regular old 3 minus 5, so that is negative 2. So I have positive 2 over negative 2, so I end up with negative 1. If I substitute in 4, the numerator is going to give me absolute value of 4 minus 5. That's absolute value of negative 1, which is 1. And the bottom is 4 minus 5, so that stays negative 1. So I have 1 over negative 1, so I get negative 1. So hopefully we can start to see a pattern emerge. If I plug in 4.5, I'm still on the left side of 5. I'm going to end up with, in the numerator, the absolute value of 4.5 minus 5, that's positive 0.5, over 4.5 minus 5, that's negative 0.5. So that's the same value divided, but one's positive, one's negative, that's still negative 1. So it would appear that from the left side of 5, my y values are just always -1. And now let's think about the right side of positive 5. So plugging in numbers like maybe 6 and 5.5. So I'll start with plugging in 6. So on the top, in the numerator, the absolute value of 6 minus 5, well, that's just 1. And in the denominator, 6 minus 5, that's just 1. So I get positive 1. And if I substitute in 5.5, the absolute value of 5.5 minus 5 is positive 0.5. And then the denominator, 5.5 minus 5, is positive 0.5. So I get positive 1. So it appears that from the right side of 5, I get positive 1, but from the left side of 5, I get -1. They are not the same value from the left and from the right, so we would say that this limit does not exist. We would say that this limit does not exist. Now that was approaching or thinking about this from a numerical perspective. If I think about this from a graphical perspective, then what's happening is as I get closer to 5, from the right side of 5, it looks like I'm a perfectly horizontal line at the y value 1. Doesn't matter what value I plug in on the right side of 5, I'm getting closer and closer to 1. And from the left side of 5, doesn't matter what value I substitute in from the left side of 5, it looked like I was always a constant function, a constant horizontal line at -1. So what's happening there is there's a jump in the graph at the x value 5. There is a jump in the graph at the x value 5. So that is thinking about it from a graphical perspective versus a numerical perspective. But the bottom line is that we did still have to do more work when I did direct substitution and I get 0 over 0. The more work was going back to what we started with when we talked about limits, the numerical and graphical approach. But they do take a little bit longer. So the ideal situation would be if we get indeterminate and we can use some form of algebra. Factor, expand, multiply by the conjugate, or combine fractions and simplify. And there may be some trig identities involved, so lots of stuff from our pre-calculus is going to be needed in this section. In this example, we're going to evaluate the limit as y approaches 0 of the quantity 2 over y minus 2 over the quantity y squared plus y. So this one's kind of different. If I think about applying direct substitution, what ends up happening is I get 2 over 0 and then minus 2 over 0. And 2 over 0 is undefined. And so we know that, just on its own, this would give us a vertical asymptote. So what we might try to do at this point, once we establish, like, okay, we're thinking about a vertical asymptote potentially happening there when I see that 2 over 0, then I start to think about what happens sort of from each side of 0. So like what's happening on the right side of 0. So if I start to think about plugging in numbers on the right side of 0, so if I consider basically y approaching 0 from the right, let's say, now what's happening is if I'm plugging in numbers on the right side of 0, getting closer to 0, like 2 divided by 0.1, 2 divided by 0.01, this quantity is getting bigger. It's going off to infinity. So if I take something small and positive and divide it into 2, it's going to get really big. And the same thing is going to happen right here. So again, I'm plugging in a small positive number down here into y squared plus y, so this number overall is getting smaller and smaller and smaller, and a really tiny number into 2 is getting much bigger. So what we have is an infinity minus infinity indeterminate form that we're working with here. So we're used to thinking about algebraic strategies when the indeterminate form is 0 over 0. But here, the indeterminate form is infinity minus infinity. We can't look at this and say, is the answer infinity? Is the answer 0? It cannot be determined. So we are going to move forward with using some algebra. We're going to combine these two fractions together. and force them to have common denominators. So we're going to do the limit as y approaches 0 of 2 over y, I'm going to leave some space there, minus 2 over y times y plus 1. So what's happening is I factored the denominator on the right hand side. I factored out a y. And so there's a y plus 1 factor that's on the right hand side. So in order to force these to have common denominators, I'm going to multiply the top and bottom by the quantity y plus 1. And now I can subtract across the numerator. So if I have common denominators, I can put this together to be one rational expression here. So I have the limit as y approaches 0 of now one fraction. I have y over y plus 1 on the bottom. And across the top, I have 2y plus 2 minus 2. So the 2 distributes, and then I have plus 2 minus 2, and that's going to end up being 0. So on the top, what I have left is 2y. On the bottom, I have y times y plus 1, so we can cancel out the y over y after I have removed plus 2 minus 2. That's important, right? So there's no other terms up here. There's just 2 times y. And so in that case, now y over y becomes 1. So what I have left in terms of a limit is the limit as y approaches 0 of 2 over y plus 1. And this time, if I substitute in 0 into the y, I get just 2 over 1, which is 2. So here we applied algebraic strategies to this other indeterminate form, this infinity minus infinity.